Hello, everyone. Good morning. So it's my great pleasure and honor to introduce Professor Erika Ábrahám. She's a great friend and one of the leaders in SMT solving and formal methods in general. Erika obtained her PhD from the University of Leiden in Netherlands for her work on verification of concurrent programs. Then she moved to the Albert Ludwigs University Freiburg, where she started work on automated solution of arithmetic problems, namely SAT and SMT solvers. And since 2008, she has been a professor at RWTH Aachen University in Germany, with main research on SMT solving for real and integer arithmetic and formal methods of probabilistic and hybrid systems. She has won way too many awards and honors, so I won't list all of them, but without further ado, please. Thank you.
Yeah, welcome on this last day to this last keynote. Well, I'm active in a lot of fields, and SMT solving is one of them. We already heard a few interesting talks and demonstrating how impactful, how powerful, how strong this area is from the practical side. What I would like to do now is to show you it is not on the practical side. It's a beautiful area. When I started my academic career in postdoc, I was thinking of how to establish my independent scientific direction. And then I thought, well, in SMT solving, there is this real algebra, the nonlinear case. It is not yet covered, so let's do that. And then after we started, we recognized how complex it is and how mathematically involved and how deep. But I didn't regret, because there are so many beautiful ideas. And today I would like to show you one of those. I'm very happy to have great collaborators. It is really a lot of fun to work with. And this is also an area where alone you don't get too far, because the problems are so complicated. Only in exchange and interdisciplinary collaborations we can solve hard problems. So what is this talk about? It is about solving logical formulas. And let me concentrate today only on the quantifier-free fragments. So we do not bear with quantifier elimination in general. Only we are interested in whether there is a solution for a quantifier-free formula. And I focus only on SMT solving, whereas only it is not really true, because SMT solving is also, or the technologies that are embedded, the algorithms, they are also from symbolic computation, computer algebra, also part from linear programming and so on. So communities exchange ideas and adapt techniques and algorithms from each other. And let me start with something which is not new. It was already in the 90s. For propositional logic, subsolvers have been developed. And what made those subsolvers practically really impactful, industrially applicable, is a very nice idea, which I show you. It is called PPLF plus CDCL subsolving. Never mind, the idea is the following. Assume we have the input in PNF, conjunctive normal form. It is possible to transform each propositional logic formula to this form in linear time and space at the cost of linearly many additional variables. Now we want to check whether there exist truth values for the propositions that make this formula true. This is a relatively small formula, and you already see by looking at it is not sufficient. So we need some automated techniques to do so. The most natural thing you could do is, well, it is a finite formula. There are finitely many propositions in it, so there are finitely many assignments to the variables that we could have. So let us explore. What can we do? Well, we have A, which can be true or false, 1 or 0, and the others true. We have a decision tree. Let us try, for example, the leftmost branch. I substitute these values into the formula, and I see it is not satisfied because some of the clauses, with the one in the middle, which is red, is not satisfied. Okay, I could take the next one. I try all of them, and at the end, I see none of them satisfies my formula, so my formula is unsatisfiable. And the easy approaches, you see the main disadvantage, the complexity. So it cannot avoid to try for unsatisfiable formulas all of the assignments, and in worst case, because the problem is empty complete, I will have to do this effort. But on some problems, on many practically relevant problems, they can be solved faster. But how? No, and enumeration or exploration is obviously not so good. Let us try with deduction. There is the resolution proof system, which tells us that if I have two clauses, and in one clause I have a variable, and in the other clause the same variable appears but with the opposite sign, then what happens? I can assign some value to this variable x. If I assign true to it, then this formula, this clause is satisfied, but the rest of the second one needs to be satisfied. And if I assign false to it, then this clause is satisfied, but the rest of the first one needs to be satisfied. So by resolution, I can derive the new threat that one of the rest, either this rest or this rest, needs to hold. Okay, not surprising. What can I do with it? For example, for this formula, look at the variable a. I can apply the resolution rule, for example, to these two clauses, and I can derive that either b or c needs to hold. Let us look at other combinations. I can also apply, for example, to these two clauses, and I can derive that c needs to hold. You'll see some resolvents are longer, some are shorter. And what can also happen is that we get the trivially true clause by the resolution, which does not give us any new information. Now, we can also use the resolution as a complete decision procedure to eliminate variables. And for that, we take all clauses where a variable does not appear, all clauses where the variable appears positively or negatively. And this formula is satisfiable if and only if the clauses where the variable does not appear are satisfied, and I take the pairwise resolvents of all clauses where the variable appears positively or negatively. And this is an equivalent reformulation of the problem, but it has one variable less. So I can apply it to all the variables, and at the end, it will give me a formula with only constants, so I can evaluate it. On our example, if I apply the quantifier elimination or the variable elimination using the resolution rule to eliminate A, then I get these clauses. And the gray ones are those which are either trivially true or they are double. So you see there are a lot. I take away the rule to have some more space, and let us eliminate also B. So I take all clauses where B appears or where not B appears and apply pairwise resolution to them, and keep those where B did not appear at all. Now I have only C. I apply it also to C. And what happens now is, let's see that from these two clauses, C or not C, by apply resolution, I get the empty clause. Now, what is a clause? It is a disjunction. And if that means one of the literals needs to hold, if there is no literal, nothing can hold. So this clause is false. It is not satisfiable. That means if by resolution I can derive the empty clause, it means my problem is unsatisfiable. If I cannot derive the empty clause, I get only the trivially true clauses, then it is satisfiable. Okay. Now, if you look at this, what we call derivation tree, what you see is we did a lot of steps, but actually what we need to derive the empty clause is only a part of it, right? It's 4 clauses and 1, 2, 3 resolution steps would have been sufficient. The problem is we do not know where this nice proof is. So we explore, apply resolution blindly. And wouldn't it be great to somehow get the guidance where this proof is, because then we could spare a lot of steps. And that means if I have a proof system and want to apply it, it is a complicated thing. I don't see where I should go. But now the great idea is, instead of blindly applying a proof system, let us guide it by exploration. We just try things out, but not fully blindly. That would just result in the 2 to the n assignment trials, but we have a look ahead. This is smart, this should be cheap, but it should avoid to do very silly things in the exploration. And this look ahead should be compatible with my proof system, because if I make a mistake by wrongly guessing despite look ahead, then and only then I will apply my proof system to generate a piece of proof. And then by further exploration guided search, I will detect those parts where I need further pieces of proofs. And I put pieces of proofs together to one proof. So let me show you an example how it works and what it means to be compatible. For propositional logic, the exploration we already know. So assume it is a very simple example, and assume that we have a look ahead, which means I check clauses where I have a partial assignment and all the literals but one are false. That means there is a single way to satisfy this clause. It is putting the last literal to true. So here at the beginning, I do not have so-called unit clauses. So I try exploring, say, well, let us try what happens if A is false. And now you see this first clause gets unit, because the only way to satisfy it is put B to true. And now I look again at my problem, and because B is true, now this clause also units. So I need to put C to true. But oops, now the last clause gets false. And this is the point where I know, okay, my look ahead didn't help me. I ran into a conflict in a partial assignment that I cannot extend to a satisfying one. And now and only now I generate a piece of proof. The proof tells me that this clause is false, and it got false because I assigned true to C, and it was implied by this clause. So now here C was implied true, which implied that it got false here. So I must have a positive and a negative combination of a variable, and I can apply resolution, and resolution makes a bridge in this implication chain. So in this case, I would apply resolution to this clause with respect to C, and I get not B. Not B is a kind of closest reason why this conflict appeared. And now if I change my search, I backtrack, and I start with assigning false to B, I can continue the search and generate further pieces of proof. Let us come back to our original example and check what happens now if we do, instead of the blind proof system, a exploration guided proof. We start now with variables assigning from the top to bottom. So now we don't have any unit clauses, no assignment yet. We assume not C. What happens? We have a unit clause here, here. So we need to assign true to A by propagation, but now this clause got false. Okay, I generate a piece of proof, by making the resolvent of the conflict clause, and why it got conflicted is it was due to the letter A, which was implied here. So I apply resolution to these clauses with respect to A, and that got C. Okay, now I know what I did wrong. I backtrack, assign true to C, propagate again in this third clause, which says that A needs to be true. And now this clause is false. And it got false because of A, so I apply resolution to these two clauses, which derives not C. And wow! This is this short proof, exactly what I need. This is amazing. And of course, I cheated it. We do not always get the minimal one, not the smallest one. It is also not always minimal, but we got nice ones. And in general, that's why it works so good. Because the exploration guided search with a cheap look ahead shows us where the short proofs are, which are the steps in our proof system that I need to derive my result. And this is genius. And because it was so successful for propositional logic, we can ask ourselves, well, this was 30 years ago, right? Nothing new. But it took a bit long till people asked themselves, can we apply it also to solve other things? Well, I love real algebra. So polynomial constraints over the reals. Now, if you look at it naively, exploration in the real domain, how do you do it? There are uncountably many numbers in the real domain. At the first sight, it looks a bit contradictory to do exploration in the reals, but it works. So before I come to exploration guided search in the real domain, let me first show you what kind of SMT solving techniques are out there. There is something that is called eager SMT solving, and I will not talk about it, but the idea is if there are logics which are not more expressive than propositional logic, then we can apply a transformation to propositional logic and then use SAT solving. And there, within the SAT solving, we have this exploration guided search. I don't have to talk about that. I don't have time to talk about that, but now there is this other type of SMT solving, which is more the traditional SMT solving. It is called lazy SMT solving. So eager means solve the theory first and then the Boolean structure. And lazy means solve the Boolean structure first and then check whether your solution is consistent in the theory. So what we do is, let me show it on an example. We have some formula like this one. And first we look at its Boolean structure. Can I select a set of constraints such that if they are true together, then the Boolean structure is satisfied? In order to do so, I replace each of the constraints by a proposition, just stating that it's true or not. So for example, x less than 0 is true if and only if A. And now I use a SAT solver to find a solution. So let us try here, the SAT solver put, for example, explore, try A false. Then by the first clause, it will imply that B needs to hold. And after such what we call a decision level, I make a decision and I check what is implied. After this, I consult a theory solver to check whether the corresponding constraints are consistent in the theory. So in this case, I would get, because A is false, I would get that this is false, so actually the larger is 0, and B is true. So this one should be true. And the theory solver will tell us it is okay, satisfiable, you can continue your Boolean search. Okay, the SAT solver could now decide, for example, what happens if C is false. My look-ahead propagation would say then B needs to be true. And now we have a complete assignment. And we ask the theory solver again, is it also consistent in the theory? And it would say, well, no. And for example, it could give back a so-called unsatisfiable invisible subset of the constraints. This constraint alone, for example, is unsatisfiable. So an explanation would be this constraint should not hold. Otherwise, the theory is broken. So now we refine this so-called Boolean abstraction by learning the Boolean abstraction of this explanation, saying that D should not hold. And now we undo the assignment and continue the search. Okay, so hand in hand, but it is driven by the Boolean search and the series and slave. The series solver just accompanies the subsolver which guides the search. This is the idea of lazy SMT solving. And here you see, because we use a subsolver, we can already use this exploration guided property in the Boolean domain. Now I come to the point, what about the theory? Can we do that exploration? And there has been a nice idea. It is called the model constructing satisfiability calculus. NLSAT is the name instantiated to real algebra. And this has the following idea. You remember we had this Boolean exploration guided search. I show you something similar in the theory. Assume we have a formula and there is a constraint in it. And now we have the Boolean and the series solver. Before you remember Boolean theory, Boolean was the master, theory was the slave. Now we want democracy. They are at the same level. They search in the Boolean, in the theory domain, hand in hand, assuring that they are consistent, that in their search they do not conflict each other. So, for example, the Boolean solver could say, well, it propagates, doesn't find anything. This should be true. Okay, and now the series solver says, I also want to do something. I would like to explore now the real space by guessing a value for X. And before it does so, it applies this smart look ahead. And this smart look ahead says, look at all constraints which should be true and which are, after substituting the already guessed values, univariate in this variable. So it's only this variable. This is something we can check relatively easy whether they are consistent. And if yes, which values I can take for the next variable, for this last one, such that they remain consistent. In this case, we don't have univariate constraints in X, so I can take any. Assume we choose 1. X equals 1. And now the series solver wants to continue the exploration, wants to find a value for Y. But what happens now, you see, if I substitute these guessed values here, X equals 1, then I get Y square less than 0, which is not satisfiable. I guess wrongly. And now we generalize this wrong guess. In this case, I could say, if this constraint holds, then the value of X should be negative. Otherwise, I cannot satisfy this constraint. And the magic is to generate this generalization. I will show you later an intuition how it is done. And then we now also generate a piece of proof, but it is a bit more encoded because we say under which conditions which should hold, and we learn in form of a clause. We learn this generalization. So we also have a piece of proof, but it is not structured into proof tree, for example, like before, but into clauses. I remember the pieces of a proof in clauses. Well, before I continue, just a small intermezzo, we also have a node solver, and it is called. And in this solver, we implemented a lot of decision procedures. Firstly, we have some central piece where we can do arithmetic computations. Based on that, we implement modules, and these modules can be composed to solver. It is not a solver, it is rather a programming library. And we have a lot of modules for real algebra. Actually, nearly everything that exists. So it is not meant actually so much to beat all the other solvers. The vision was to generate a solver where we can easily try new procedures, we can combine them and also apply in teaching and in research education. And you see here, our focus is here. This is the actually only complete decision procedure in use for real algebra, the cylindrical algebra in decomposition. Yeah, I don't want to go in detail here, just that we can combine these modules to solver conditionally depending on the input problem. We can choose solvers, we can introduce parallelism and so on. So if you like to play a bit with the solver, it is open source, publicly available, and easy to extend. Okay, what did we see until now? Because now I come to the main point. So what we have seen is we have this exploration guided search, extremely efficient in SAT solving, and by that in lazy SMT solving in the Boolean part. We have in MC that not directly within the modules, but the kind of globally by putting the pieces of the proof in clauses. And then I can use that by propagating in those clauses. But what we do not have is what is here with the theory. So can I also apply this very successful exploration guided search just in the theory to speed up the computations for conjunctions of constraints? And because we do it for real algebra, it's a bit complicated. To give you the intuition, let us first start with an easier thing with linear real algebra. So there is a method to extend there also the search to this exploration guided way. And the main idea is not to use the clauses to store the pieces of a proof, but inside of the theory solver, use a data structure to maintain what pieces we already have and continue until either we have a solution or we have a full proof for unsatisfiability. And this way, we save the work of learning clauses and all the propagation in those clauses. And also, this information is then local to this proof. We could learn pieces, but don't. Okay. So now I show you the main idea on the example of the Fourier-Motzkin quantifier elimination method. And I first show you how it works in the traditional lazy SMT solving to get the idea what it is. So assume now we search and the Boolean search that these constraints should be true. Now what happens, the Boolean solver asks the series solver, are they consistent together? And the series solver says, well, look at it. We look according to a fixed variable order. So assume x1 first. And it checks. Satisfiability in x1 is checked by reformulating the constraints. They are all linear, so I can bring x1 to one hand side. That results in a set of constraints which define lower bounds on x1 or upper bounds on x1. And the reals are dense. That means as long as all lower bounds are less or equal or upper bounds, there exists a value in between. Unfortunately, these bounds are symbolic, so I cannot decide whether there exists a value in between because it depends on the value of x2. But I can symbolically state that in order that there exists a value for x1, all lower bounds should be less or equal or upper bounds. Okay, and these constraints I just generate. For this lower upper bound pair, I get this one, x2 less or equal to x2. And for this, I get another one. Let us simplify them. And now look at the next variable, x2. It has also lower bounds and upper bounds. And there exists a value for x2 if and only if all lower bounds are less than or equal or upper bounds. I generate the constraints and I get this one. 1 less than or equal 0 is unsatisfiable. After eliminating all the variables, I have only constants, I can evaluate them. I see it's unsatisfiable. So now we can return unsatisfiability and can generate an explanation by moving back and checking, so which were the constraints and which were the actual steps that I needed for this piece of proof. And we see, okay, I actually would have needed only 2 combinations to generate this proof, but I did not see, right? So I generated also these because I do not know where the short proof is. Now, what would happen in MCSAT? In MCSAT, I would, before I apply my proof system, also try to explore. So I would say, well, what value can I take for x2? I have one constraint that is univariate in x2, says it should be less than or equal to 0. And okay, let us take 0. What happens if we take 0? I substitute it into the other constraints, which get univariate in x1. So I have here x1 should be between 0, 2 is also a lower bound, and 0 is an upper bound. So it should be between 2 and 0, which is impossible. There is no value for x2, which can extend this value for x1. And now I can check which are the bounds that are conflicting and apply my proof system only there. Okay, so I apply only to derive that if these 2 constraints hold, then this lower upper bound combination should define a non-empty interval. Okay, I did something wrong for x1. Now I can apply, okay, simplify this. I can apply Boolean propagation to this newly learned clause because these constraints are true. It now says that this should hold. And I repeat the exploration in the theory, which tells me, well, which value can I take now for x2? This was already there. It should be at most 0. Here I say it should be at least 1. There is no possible value for x2. So now I know I need to apply my proof system again to derive that the problem is unsatisfiable. And you see the magic happened again. We did not do these unnecessary proof steps. Just by doing exploration and the smart look ahead, which is compatible with my proof system, I could detect where are the important proof steps that I need to do in order to derive unsatisfiability. And this is really a very nice idea. So exploration makes sense also in the theory, even though the theory is an uncountable domain, because I have a finite generalization. So I can generalize the wrong guess to a set such that I only need finitely many generalizations even to derive unsatisfiability. And then what we thought is, thereby MC that it is a kind of global. I learn these pieces of proofs in clauses. And even though the method is extremely powerful and can solve a lot of problems also in the automatization, but these clauses, if the problems are large and I learn a lot of them, they get just blocking the process through propagations in these clauses, because here they seem easy. But in reality, when these get, I will show it to you, real algebra, semi-algebraic sets, this is not so easy to generate them, not so easy to propagate in them. So could we do it differently? This was the original one, blindly doing unnecessary proofs. This was MC that we get the nice proof, but a kind of with intermediate steps. So let us do it only in the theory. Exploration guided theory solving, using the data structure in the theory to remember the proof steps. Okay, we do the similar thing like MCZ. We start exploration, but we now have a set of constraints, and we remember a proof tree. So I again start. What could be the value of x2? I have only one univariate. Again, it should be non-positive, so I can choose, for example, x. I want to assign x1. I detect there is no value for x1. It is the same as before. And I recognize that these two constraints here are conflicting under this guess for x2. And I apply a proof step. But I don't learn as a close now. I'm only in the theory. And I just remember this in a proof tree, in an internal data structure. So I do not need propagation. And I continue. So now I simplify this constraint. And I know this guess was wrong because it conflicts now my current constraints. So I undo, I check now, okay, what can I do for x2? And I see nothing because these boundaries conflict each other still. I apply one more proof step and I have my proof tree without interacting with the Boolean case. Okay, not closes, it is a proof tree. I generalized and I can now give back to the SAT solver that these three constraints together should not hold. And that is what I learn as a close to refine the Boolean extraction. Good. So here we have the global picture on the example of the linear arithmetic. Exploration guided search helps us to find short proofs in the Boolean domain or in a kind of mixed way, learning pieces of proofs as clauses or in the theory. And I would like to show you the real algebra. It's complicated, I cannot go into detail, but at least the intuition, and I hope I will succeed despite the fact that the things are really complicated, to show you at least the main ideas. So, what is the key idea for decidability in real algebra? In real algebra, we deal with polynomials, polynomial constraints over the reals. And if we have univariate constraints, like this polynomial is just one variable x, we call univariate, then the key to decidability is this polynomial has finitely many real zeros. And between two real zeros, the sign of the polynomial cannot change. That means I have finitely many so-called sign invariant regions if I'm able to determine the zeros of the polynomial. And we cannot determine it, we say we isolate the real zeros. We can represent them symbolically without graphing them exactly, but we can compute with these symbolic representations. Even though I do not know how this polynomial's function looks like, if I know the zeros, then I can plug in the zeros and samples, any samples between the zeros and on the left and the right, I have finitely many because there are finitely many zeros. And if one of them fits the sign condition, in this case that it is negative, then I have a solution, otherwise there is none. Okay, nice. So it is not that easy because here, for example, if I have this polynomial, it's radicals in the solution, square root of 2. And in general, they are algebraic numbers, not so easy to represent. There are different representations. For example, I can represent this zero as the polynomial and an interval such that this is the only zero within this interval. It is a unique representation, but you can think already that it is not that trivial to compute with it. But it is a unique representation. What I can also do, I also can say that I mean the third zero of this polynomial, 1, 2, 3. This is also a unique representation. Of course, I have to ensure that there are at least 3, such that this so-called index root expression is valid. and well defined. And there is, for example, also top encoding. I take the first three derivatives of the polynomial. I evaluate it at that zero, and I take their signs. And this is also unique. So this polynomial means I mean the zero at which the first derivative is positive, the second derivative is positive, and the third derivative is positive. It is also unique, but not so easy. So you see why I would like to avoid propagation involving these representations. Okay, we have an idea how to do the univariate case. What is about the multivariate case? Assume I have these two constraints, and now we switch in our minds. I do not depict anymore the curve of a function. I depict their real zeros. So for example, if you consider this one, where this polynomial gets zero is this circle here. And why is it good to use this representation is because the zeros divide this so-called sign invariant regions. Within this circle, the sign of this polynomial will be invariant. And for example, in this area here, both polynomial signs are invariant. And now, like in the univariate case, we have seen that the number of different sign invariant regions, I can have finitely many to cover the real line. Also, we can have finitely many to cover the Euclidean space. So now there is the cylindrical algebraic decomposition. I told you, and this is a surprising fact that till today, this is the only method in use that is complete. And we know that the purely existential problem is solvable in exponential complexity. This one is doubly exponential. And we have no exponential in use yet. It is the same surprising then for linear real algebra, conjunctions of polynomial constraints are solvable in polynomial time. And there exists here today, as far as I'm aware, one complete method, which is the ellipsoid method, but it is polynomial worst case, but also in average case. So it is more expensive in practice than the exponential, the worst case exponential simplex method. So we have a lot of space here to find out things yet, even though the problems are so old. We don't have yet the solutions that we wish to have. So the cylindrical algebraic decomposition does the following. It decomposes the state space into sign invariant regions that are ordered in cylinders. So for example, this one is a cylinder, and you see I have here a sign invariant region, here, 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 and they are stacked. That means if I choose within this cylinder, for example, for x the value of 2, and I substitute it in my polynomials, which results in this line, then I can determine the zeros. So I can pick samples, which are the zeros, and between the zeros, to grab a sample from each of the sign invariant regions in this cylinder. And the cylinders are determined such that I can get any value here, I will run through the same sign invariant regions, because the number, multiplicity, and order of the real zeros does not change. So you see here, I have this, the real zeros of the first one, which is less than the real zeros of the other polynomial, which is less than the second zero of this one. And this cylinder boundary are there where this changes. Here, for example, these two zeros become equal. So now if I have these cylinders, I just pick any value in a triangular order to get samples for each of those so-called cells in all the cylinders. And you see there are a lot of them. And I can check all of them, whether any of them satisfies my formula. If it is the case, I have a solution. Otherwise, there is no solution because I covered all sign invariant regions by a sample, even though in worst case there are doubly exponentially of them. I can generate this by a two-stage approach, a projection phase and a construction phase. I don't explain it, but I will show it to you on an example. And just to remark, we did a lot of work on these methods. And the result of this is what I want to show you on the very end, is the modification of the decomposition, where we use this exploration guided idea, and then we move from decomposition to covering. Okay, but first let me show you what happens if I use the cylindrical algebraic decomposition. Now we move back to lazy SMT solving. So I search for a Boolean solution and I check it in the theory. I get a set of constraints. For example, these two, which we already know. Now the projection phase will extract the polynomials from these constraints and project them, giving us a set of polynomials in one variable less, without the variable that I project out, with the wonderful property there, and this is now magic, that these polynomials have zeros which define the cylinder boundaries. Okay, so if I can isolate the zeros, I can determine the cylinder boundaries. I take the zeros and samples between them. Then I substitute this into the polynomials, again isolate the zeros, again take samples between them, evaluate, and I can check satisfiability. Oh, this was the lazy SMT approach. Now what happens in MCSAT, or for real algebra it is called NSAT, means I guess values, and if I guess wrongly, then I want to generalize my guess, which is a point, and it is a point in a cell in the CAD which does not satisfy the sign conditions. So I want to generate a description of the cell in which the point that I guess and which does not satisfy my formula lies in. So if I would do it naively, so assume this is the value that I guessed by exploration, does not satisfy my formula, and assume that I have here 3 polynomial constraints, and for example, the green constraint here is violated in the area which is colored green. So that means that this sample cannot be extended to any satisfiable sample because these extensions would violate the green one, these ones. So at every point, one of the constraints is violated. Only in the white areas, all constraints are satisfied. So in the naive case, I would consider the cylindrical algebraic decomposition of the 3 polynomials, which would give me this cylinder where the point lies in. So I could generalize this sample to this interval here. And already the NSAT approach was smarter because it could identify polynomials which together already assure that I cannot extend my sample, which would already yield in a larger generalization. Because here, for example, I don't consider this one which would cut my space the smallest. So if I neglect it, I get a larger generalization. And now what we did is we used the exploration guided idea to further improve it. And for example, this example, we could generalize it to this set, which is much larger. I don't have time to explain in detail what happens, but let me show you on an example. So we are in lazy SMT solving. The theory solve, the Boolean solver told us that these constraints should hold together. Now it doesn't matter what they exactly are, but important is that, for example, the green constraints are violated here where the space is colored green. Now we have a pure theory solver. And we want to check consistency in an exploration guided manner without using these clauses in an internal proof structure. So what do? We start exploring. This would be what the CAD would give us. And I want to have it better with less samples, less details, only what is really relevant. So we start guessing, for example, this value for x1. And because we can substitute it in the polynomials and we can check the sign condition, we see that there is no extension. And now we generalize it, but in the generalization, I do not need to consider all polynomials, because then I would generalize it just until this point here. But I can see, well, the blue polynomial alone cannot be satisfied. I can cover this whole line. All points are violated already for the blue one. So I will be able to generalize it to this set by identifying a covering of this real line by unsatisfiable regions for, in this case, only for the blue polynomial. And now I consider then another exploration outside of this area. For example, we can take this one. And now, again, my search will tell me I cannot extend it, so only this is the satisfiable region. Another question is, how can I generalize? And again, I can generate a covering of this line by different polynomial sign invariant regions, which cover it. For example, by the green one and the red one. And I see that I do not need this one to consider this one, and also not the blue one for this covering, which will allow me to generalize it to this region as long as the chain still remains a chain. I can apply the generalization. And now the main difference is to the CAD that I have here a covering. I, so to say, consider different pieces of proofs from different CADs, depending on which polynomials I just need, and I relax the decomposition to covering. By that, I get a much more coarse proof. And I remember this proof internal in a data structure, which tells me which part of the space I already covered and which not. And in this case, the problem is satisfiable. So if I would guess outside of this another sampling, for example, here, I could find a satisfying solution. I'm aware that it is not possible to give the insight, but perhaps what you got is that this exploration-based search is so powerful to find the areas where I need to apply a proof system instead of applying it blindly. Exploration and smart look ahead that is that fits to my proof system helps me to find shortcuts, even without guarantees. In practice, it is very efficient. And what turns out, for example, in the case of real algebra, here you see the model constructing satisfiability checking runtimes with our solver, and here the covering runtimes. And you see these lots of timeouts. They are kind of orthogonal. And the reason is that in these methods, some computations in the projections might be so complicated that only this single computation already kills the solving process. And it happens at different points. So they are orthogonal and competitive. So this search-based or exploration-guided methods are really good. We implemented it once in our solver, and this was in 2020. And it was quite good, but our solver is not so good in the Boolean case. So, and also the competition benchmarks are kind of restricted in their variety. So we were not that good. But then the CVC5 team here is represented widely. So in 21, they won the competition, and the covering was implemented in this year in the solver in combination with, as far as I know, some linearization approaches. So it turned out to be very good. And then next year, there was another solver. This just happened popped up from nowhere. It is called Z3++. And they had a bug. Otherwise, they would have won the competition. Now you can ask, what is this? If you look at these numbers, they are so much better than all the others. What do they do? And actually, I did not find any publication of the method in this tool, and it is open source, so one could look at, but I did not make the effort to reverse engineer what they are doing. But from the system description, what I get is that they do an even more exploration-based search. They do a kind of cell jumping in CAVs. So they explore something, and if it does not fit, then they change one dimension and jump between cells and try this way to find satisfying solutions. And indeed, the year after, they repaired this bug and they won the competition. So exploration-guided search is very effective. And what we did this year in the competition is we implemented the covering, extended it for quantifier elimination. And this won this year for the competition for quantified real algebraic formulas. It is much better than the others because the pieces of the proof that we need, guided by exploration, allows us to leave away a lot of unnecessary steps and find the relevant parts. And this is really genius. So I hope I could convince you that sometimes some ideas, they are more than a sum of pieces. It might really give you something that is very efficient. We did not export everything yet. So also in MCSAT, we could even combine these two. Unfortunately, or fortunately, we have more ideas than we can implement. So it is a lot of fun, but also a pity that not all ideas go into practice due to time and missing resources. But yeah, already what we did shows that there is still a possible. And I'm at the end of my talk. I hope despite the theoretical complexity, I could give you at least the basic ideas and the intuition, and also to show you that there is really beauty in research. And if you do the right things, it does not only work, but it also shows you the inherent properties of the problem that we are trying to solve. Thank you for your attention, and I'm there for questions.
Thank you for a beautiful talk. Questions, please? Yeah, let's see.
Thank you for an incredibly clear and thoughtful talk. I really appreciated your walk through how such a complex process works. And that's why I wanted to run something by you. So in the recent past, about a year or so ago, the U.S. National Science Foundation had a call, and the preface was the correctness of scientific computing. And the premise was that we have made tremendous leaps and bounds in using things like SMT, exactly as you just highlighted. And yet it has not been adopted in those communities the same way that we've seen adoption in things like aerospace or railways or things like that. So I would love your perspective on what is needed to get to bridge that gap, right? So that people who use real arithmetic, right, in other domains find this more accessible. So it becomes a routine thing that's expected as a part of that, the way it is in other areas.
So I think the first and most important thing would be to put in more resources in the research, because we are still not there, as I told you. We are still missing very basic components in understanding the problem itself. So as long as we cannot implement the non-complexity bounds with a sufficient efficiency, we are not yet understanding the problem. And I'm a bit skeptical in this research direction, making science the economical thing where we go for speed, we need to achieve something fast, and it should be solved next week. These are hard problems. They need time. They need people to discuss and brainstorm without having a complete application in mind. So I think as long as we focus on speed and higher and faster, this is not the way how these problems are solved. But I'm convinced that we are getting there and that it will get practical applicability, of course, because the problems are hard. It will not be anything that we will solve in no time, but I'm convinced that they will get applicability and money and resources and good students.
There's a question over there.
Sebastian, you can talk loud. So there is something unclear in that algorithm. I do not think that it is singly exponential. We were discussing this. So the complexity bounds are very mean because sometimes we forget a small tiny thing like number representation, complexity of representing numbers, and you already have the wrong complexity stated. And we were discussing this. I need more time to look at it exactly, and also the help of the computer algebra people to understand. But the common opinion in the moment is it is not singly exponential. Yes. Yes, so between this one and this one, you mean? So here, you first search in the Boolean domain, and in the theory, you do not explore. It is just some proof system that you apply blindly. And the idea is to bring also exploration in this theory proof system, guidance, that you don't apply all the steps that the quantifier elimination dictates, but elect those which are important for your proof. So this is the main idea. So thank you for the question. This is the very basic idea to do what we do here for the exploration in the Boolean domain with the DPLL, CDCL, that we first explore and apply the proof system only when we see need for it, to do it also in the theory. And this was already suggested in the MC-SAT approach to do it, but there the proofs were not maintained as a proof in a dedicated proof structure, but rather learned as clauses. So the kind of the proof is represented between the Boolean and the theory part in a mixed way. And in order to see what kind of proofs, which parts of the proof are already there, I needed the Boolean propagation, propagating in these clauses. And what we suggested is to divide it clearly and apply the exploration-based idea also in the theory, purely without the Boolean part, without learning clauses, saving it in a proof structure.
More questions?
Yep. You can talk.
Is there any such a collection of clean algorithms like this for a model counter or generalization model counter? I would like to have a estimation of large
Yeah, this is a very good point. So direct model counting, of course, in the real doesn't fit because there are uncountably many possible solutions. And also measuring the size of sets is a non-trivial problem. But I was recently thinking about it, that it would be indeed very interesting to have some estimates or some indications, but if they became meaningful or anything with guarantees, I don't know how to measure it. Because you have these sets, you can generate them, the satisfying cells. Yeah, I don't know how to give estimations for size of satisfiability. That's a very good question.
Over there was a question over there. Yeah, thanks for the great talk. I think it's about search, and with the search on the approach, SAT is a problem, you may not find a solution. On the other hand, our control is very successful. There was a very popular blog. The title is "The Capitalism of AI," the capitalism by Saltman. The main thesis of the blog is about search and learning. And also, from the learning community, there's about declaration versus declaration. So when we draw something, we may learn something during the process. So yeah, the point is, also, some people are working on, for example, you're learning for bounds and bound. We may find something efficiently or effectively during the search process, finding the best branch or the good branch to search, or we may stop search some branch earlier because we have a good farming function. Yeah, so the question is, what do you think about learning approaches for SMT and SAT?
So do I understand right? The question is whether you could use AI methods to speed up search?
Yeah, basically about search and learning, like comparison versus declaration. So how about learning through this?
A very good question, and a very good challenge for the AI community, because learning is based on where you can provide an input that has enough details and characteristica to learn the output. Now you take a formula and assume proposition logic formula. You just switch one proposition and negate it. And the whole formula gets a completely different meaning. And in order to train a network, for example, which formula is satisfiable, which not, due to these very, very sensitive changes between syntax and semantics, you have to train so long that your life is not enough. So what is still missing today is to find out which characteristic information we should take from the formulas in order to learn. But there are a lot of opportunities still to use AI, which is not yet explored. For example, isolate trio roots of polynomials. I could imagine that this would work fine, because that is a different problem where changes, for example, in the constants are, of course, continuous changes in the output, so that could work well. It is not yet well explored, but I am aware of works who are going in that direction and try to explore it now. But we have to make sure that this is only strategic guidance, and we cannot rely on that, of course, because we want to maintain correctness and completeness.
Great question. And I've done a lot of work in this space, so we can help.
That was a
question over
last
there.
attempt. Can you talk loud enough?
I think it's better if we go down.
Very good question. So currently we none. We do not do anything. We only do the expression guided here. So this is kind of future work. And the main difference is a very good observation that here we learn everything and maintain all pieces of proofs forever. And here we just maintain it in the proof tree. Once we are done, we throw it away. And if next time something similar comes, we derive it again. So what would be meaningful here is a kind of if there are information which I think this part of proof, this might be relevant also later for other proofs, then I could learn it. But it is not yet implemented. So what is meaningful to be learned, it is not yet clear. Perhaps we can use AI.
Thank you for the very nice talk. Presented some compelling examples where the short look ahead to how the theory works. And I was wondering if you have theory, if you could choose your own theory, if you could design theory where it had this property like short proofs or short replication, what properties would you give this new system? And then kind of related question, how optimistic are you that the insights from proof complexity or paradox complexity can be translated to solvers?
Yeah, thank you. Very interesting questions. And to be honest, I do not know the answers. What I know is that, and I tried to generalize, I had now two examples, what it means to be compatible between the look ahead and the proof system. What it means in general, how can we formalize it in mathematics? I don't know yet. But I was thinking about it, and it is a very relevant question. And the same holds for guarantees regarding the size of the proof that we find by exploration guidance. I cannot give you any guarantees, even for proposition logic, I cannot give you any. And in worst case, of course, it's exponential. But it would be very interesting to find some characterization, or also conditions, under which conditions can I assure that at least I have a chance with the right heuristic to find the shortest proof. I don't know. So it is still to be understood, but very relevant question. Thank you. I think you all would like to have a coffee.
Yeah.
So I thank you for your attention and wish you a nice rest of the conference and also a great home. Thank you.
Thank you very much.